Hi folks, welcome back to part 3 and also the last part of the covariance matrix adaptation evolutionary strategy. This had been a 3-part series. Previously in part 1, we talked about the general idea behind how we can build an evolutionary strategy based on repeatedly sampling from and then updating a multivariate normal distribution. And then in part 2, we started talking about the actual CMA-ES pseudocode as described in the Hansen 2016 paper. And we went over the first 2 sections of the pseudocode. That is the sampling section, and then the recombination, in other words, the update of the mean. And the idea for today is to go over the 2 remaining sections, and we are going to eventually conclude with a simple demo. So let's get started. You might remember from part 2 that we specifically talked about separating the step size from the covariance matrix, such that now we have 2 components for the covariance part of the multivariate normal distribution. One is the quote-unquote normalized covariance matrix, which is labeled as capital C, and henceforth simply referred to as the covariance matrix. And the other is the scaling scalar, which is labeled as small sigma, and referred to as the step size. And we also discussed about the motivations behind this separation. And one of them was that these 2 measures rely on fundamentally different kinds of information for the updates, and therefore we would want to update each of them independently of the other. And indeed, if you look at the 2 remaining sections, you can see that section 3 is step size adaptation, and section 4 is the covariance matrix adaptation. So we're going to talk about those 2 sections, and hopefully after today, you're going to have a better understanding on the difference between the 2 update mechanisms. Let us begin by talking about the step size adaptation section, which consists of these 2 kind of scary looking equations. And in order to tackle them, let us first try to develop an intuition regarding what are we trying to accomplish by changing the step size. When do we want to increase it and when do we want to decrease it? Again, if you remember from part 2, we have been talking about step size as this caution metric because, well, the step size being the scaling scalar, the scaling factor for the covariance matrix, essentially decides how far away from the mean do we want to explore, and by extension, how aggressively do we want to explore the parameter space. And generally speaking, we want to be more aggressive with the update, with the optimization, if we are somewhat certain that we are going to be following a good direction of optimization in the parameter space. Because in that case, if we know that we're going to be following a good direction, increasing the step size and thus being more aggressive with the update is going to result in larger updates along this good direction, which would just get us to the optimum faster. So the next obvious question becomes, how do we know whether we are going to be following a good direction of update? Well, every iteration, CMA-ES makes an update on the mean, right? So let us consider a sequence of those means. So say this is like the mean for the first iteration. This is the mean for the second generation and the third and fourth. And between every 2 successive means, we're going to get a vector leading from the old mean to the new mean. And therefore, we also get this sequence of vectors. The key here is actually trying to figure out whether these vectors align, essentially, with one another. Because every single update vector had been one of the better update directions according to information available to CMA-ES at the time. We made sure of that by using the ranking and then the weighted average. So if all these kind of locally good update directions all align with one another, then that's a reasonably sure indication that the direction that we had been following for the past few generations is a good direction, and we're going to continue following that direction. And in that case, we would want to increase the step size. This sequence of mean update vectors is known as the evolution path. And in order to better understand the interplay between the evolution path and the step size adaptation, let us look at 3 scenarios. Now, this last scenario to the right is the scenario that we had been talking about. In this case, the vectors align with one another, and therefore we know that we had been following a good direction, and we are likely going to be continuing down that direction. And in this case, we want to increase the step size to get larger updates along this good update direction, and therefore accelerate the optimization. This first scenario to the left is the exact opposite. In this case, the vectors contradict one another, So we are not so sure that we had been following a good direction of update, and we want to decrease the step size to be more cautious. And this is really just the middle point between the two extremes. And also notice that an easy way of measuring whether or not the vectors in the evolution path align is to simply sum them up. Because vectors are directions, and if they align, then their sum is going to result in a long vector. And if they don't align, then their sum is going to be just a short vector. So again, in summary, we want to increase the step size if the sum of the evolution path is a long vector, and we want to decrease the step size if the sum is a short vector. And in order to decide whether or not the vector sum of the evolution path that we have computed can be considered as long or short, we need to compare it against some sort of reference. And in the case of CMA-ES, this reference is actually the expected length of the sampled vectors taken from a standard multivariate normal distribution. So a distribution with zero vector as the mean and the I matrix as the covariance matrix. And what I mean by that is that if you were to, so given this normal distribution, if we were to sample an infinite amount of times from it, what is going to be essentially the average length of the vectors that we have sampled? And that is actually a constant whose number depends upon the dimensionality of the parameters. So we can, again, compute this at the beginning and just reuse the same number throughout evolution. And given this reference, CMA-ES compares the reference against the vector sum of the evolution path according to this equation. So as you can see, the denominator here is the expected length of the sampled vectors, which we had just been talking about. And the denominator here is actually the length of the vector sum of the evolution path, which we're going to talk about in the next slide. So if the length of the evolution path sum is larger than the reference, this ratio is going to be larger than 1. So this expression is going to be positive, and essentially this expression is going to be a number that is larger than 1. So the step size, small sigma, is going to be scaled up, and vice versa. Okay, now we can return to evolution path and get into a bit more detail with how exactly do we update the evolution path. Fundamentally, what we are doing is what is called a rolling sum. We keep this accumulator p sub small sigma, and every iteration we just add the update vector on top of it. And it should be fairly easy to see, fairly easy to understand that at any arbitrary iteration, this p sub small sigma is going to represent the sum of all the update vectors up to this current iteration. And also the update vector is just the y sub w term from section 2. That is the recombination section. So you can check it out. That was the vanilla rolling sum. And one problem with the vanilla rolling sum is that it considers all update vectors equally, regardless of how far, how distant they are into the history. And that is problematic because intuitively, we want to favor the update vectors that are more recent, because those represent our current situation more closely, right? And therefore, they should be more informative with our update. And in order to implement this bias, what we do is that we include this scaling term in front of the accumulator. The c here is actually another hyperparameter, and this entire scaling term is guaranteed to be in the range between 0 and 1. And if you expand this expression, it should be fairly easy to see that the further away an update vector is into the history, the higher the power it gets for its scaling scalar. And because the scaling scalar is a number between 0 and 1, the higher power of it means actually smaller scaling scalar. So it is kind of tuned down in the bias. One additional modification that we need to make on top of the vanilla rolling sum is that we need to actually scale the update vector before being able to add it on top of the accumulator. And the reason for that is that the update vector itself comes from the sum of the sample vectors. And because those are samples, they're going to have their own variances. So unless we scale the sum of those samples, we are just going to be continually accumulating the variance and make our algorithm unstable. So this term under the square root is actually used to cancel the accumulation of variance. Deriving this term can actually involve a bit of math, so I'm not going to go too deep into the details. And if you want to know more, you can check out the page 17 on the Hansen 2016 paper. And these here are just some additional hints that you can refer back to when checking those derivations. Okay, so now we have only the c to the power of -1/2 term left to explain before we wrap up this formula. Remember that capital C represents the covariance matrix, the quote-unquote normalized covariance matrix, which kind of encodes the directional bias of the distribution from which we take the samples. So why is this C term here? And moreover, why is it raised to the power of -1/2? In order to understand the intuition, let us first remember that the length of this p sub small sigma term, the evolution path, is eventually going to be compared against a reference. And that reference, as we just discussed, is the expected length of the vectors sampled from a standard normal distribution, which has I matrix as the covariance. In other words, its covariance matrix has only ones along the diagonal. And if you imagine its shape, it's just going to be a circle or a sphere. And having this I matrix as the covariance means that if we want to sample a vector of a certain length from the standard normal distribution, it is equally likely that we get this vector along any direction. Therefore, we say the standard normal distribution has no directional bias, and therefore the length of the reference is directionally independent. However, the same cannot be said for the update vectors, which consist of the evolution path, because they come from the sum of sample vectors, which themselves are sampled from this distribution, with C as the covariance matrix. And if you remember from part 1, the entire point of CMA-ES is to adapt this C, this covariance matrix, such that the shape of the distribution is biased along the directions it found promising. So instead of a circle or sphere, the shape of the distribution from which the update vectors y sub w come from would often be an ellipsoid, maybe something that looks like this, for example, which is clearly not directionally independent, because we are more likely to sample long vectors along this direction and less likely along this direction. But how does this kind of directional bias affect the comparison between evolution path and reference? For example, say we are at the first iteration in CMA-ES, and our calculation gives this update vector. And because we're at the first iteration, our evolution path consists of only this one vector, and we just simply compares it against the reference. At first look, this would appear to be a long vector, right? And according to what we've just discussed, would therefore suggest increasing the step size. But if we think about it, the length of this vector is largely because its direction aligns with the biased direction, because it's more likely to sample long vectors along this direction, as we just talked about. So if we directly compare this vector coming from a directionally biased distribution against a directionally independent reference, it is kind of not a fair comparison. So for this reason, we want to cancel out this directional bias, kind of normalize, quote-unquote, y sub w with respect to direction, you might say, before adding it to p sub small sigma and comparing it against reference. In other words, we want to make this C, kind of, into I, the I matrix. And we know exactly how to do that, because we already talked about the affine property of normal distribution back in part 2, and this equation here essentially shows how this is done. And again, in conclusion, the C term is just there to cancel out the directional bias in y sub w and make it directionally independent. And with that, we are ready to conclude the step size adaptation section. And just as before, we are going to give a quick run through of the section before moving on, just to connect everything together. This first equation, equation 43, maintains the evolution path p sub small sigma by what is essentially a rolling sum. The 1 minus c term here is there to ensure that more recent update vectors are given larger weights in the rolling sum. The square root term is there to cancel out the variance accumulation incurred by the update vectors. and the C term is there to make the update vectors directionally independent. And after we obtain this evolution path, we're going to calculate its length, and we're going to compare the length against a reference, which is the expected length of the vectors sampled from a standard normal distribution. And if this ratio is larger than 1, this entire expression is also going to be larger than 1, and step size is going to be scaled up, and otherwise it is scaled down. The intuition being that if the evolution path results in a long vector, it's indication that the update vectors within the evolution path more or less align with one another in terms of direction, which is in turn an indication that we are following a good direction of update, and we want to increase the step size to essentially accelerate the optimization, and vice versa. So now we have only the covariance matrix adaptation section left to explain. And in order to explain this section, let us first look at equation 47, which is the equation that actually updates the covariance matrix. And if you observe this equation, you may notice that this equation is really just a weighted average among 3 terms. This first term here is actually just the old covariance matrix from the previous iteration, and it's just there to ensure that we make a gradual update instead of just changing directly to the new value. And we don't need to worry about it too much. What we do need to worry about, though, are the second and the third update terms, and they represent the so-called rank 1 update and rank mu update respectively. The terminology might be a bit confusing, but I'm not going to explain the reason behind this terminology, and you can refer to the Hansen 2016 paper for more details. But for now, just know that this is the rank mu update, and this is the rank 1 update. And between the 2 update terms, the rank mu update is actually the easier one, so let's start there. If you remember the simple covariance matrix update that we explained back in part 1, then this rank mu updates term is actually pretty similar. And there are only 2 minor differences. The first one is that instead of x minus m, we now use y, which, as we explained earlier in part 2, may be considered as a standardized version of x, because, well, mean and the standard deviation, right? And also, by the way, we don't need to have a separate equation calculating this y, because conveniently it comes from equation 39, which again kind of echoes what we said earlier about the versatility advantage of separating this big sampling into smaller submodules. So that was the first minor difference. The second minor difference is that instead of a fair average, we use a weighted average, similar to how we did back in the recombination section for the mean update. And the weights used in the rank mu update average is actually just the modified version of the weights that we used back in the recombination section. And here is the kind of modification equation. So in general, if you understood well the intuition behind the simple covariance matrix update, then this rank mu update should be fairly easy to understand for you. But there is a problem to this rank mu update, which is that it is based on taking the dot product between a vector and its own transpose. And I like to call this calculation the quote-unquote dot product square. And this calculation, this dot product square, is actually insensitive to sign. So y dotted with y transpose is equal to negative y dotted with negative y transpose. And in order to see why this presents a problem for the covariance matrix update, let us consider 2 different sequences of update vectors. Here to the left, we have v, then w, then v, then w. And to the right, we have v, then negative w, then v, then negative w. The only difference between the 2 being that the signs for the second and the fourth update vectors are negated. Now, if we were to use only rank mu update and simply take the quote-unquote dot product square of the update vector each iteration and average it with the existing covariance matrix, then we would get exactly the same covariance matrix at the end of 2 sequences. Because w dotted with w transpose is exactly the same as negative w dotted with negative w transpose. And as you can see, for both sequences, at the end, we get this kind of flat ellipsoid for the distribution shape. But intuitively, we know that for 2 different sequences of update vectors, the eventual outcome of the covariance matrix should be different. And just intuitively, because on this left side, all the update vectors kind of go along the vertical direction upwards, that should be considered as an indication that the upward direction is the direction for fitness improvement. And we should expect, more or less, to get the shape of the distribution to be this kind of thin ellipsoid instead of a flat one. But nevertheless, because the quote-unquote dot product square calculation is insensitive to sign, we get the same flat ellipsoid for both sequences. We want to correct this and somehow make the covariance matrix encode the directional information instead of ignoring it. However, we also know that the update for the covariance matrix has to involve this quote-unquote dot product square calculation, which is always going to be insensitive to sign. So what can we do in that case? One idea is that we can encode the sign information into the vector before we do the dot product square calculation on it. And the eventual implementation of the solution actually ends up again being a rolling sum of the update vectors. And because it's just a sum, it does recognize the sign difference. And if two vectors have opposite signs, they're going to cancel each other out in the sum. And after we obtain this rolling sum, we are going to, as usual, take the dot product square of this rolling sum and include it in the covariance matrix update. So that is what is called the rank 1 update. This is the rank mu update, and this is the rank 1 update. And the equation for maintaining the rolling sum is actually pretty similar to what we used back in the evolution path for the step size. The only two differences is that firstly, we use a different hyperparameter for the learning rate, and secondly, there is no longer the C term, because as you remember, the C term is there to cancel out, to make the y sub w, the update vector, directionally independent. But in this case, we specifically want to encode the directional information, and therefore we no longer need to make it directionally independent. So the C is no longer there. And as always, a quick run through before we conclude this section. The update for the covariance matrix is really the weighted average among three terms, the old covariance matrix, the rank 1 update term, and the rank mu update term. The rank mu update is essentially the same as the simple covariance matrix update that we used back in part 1. And with the exception that instead of a fair average, we now use a weighted average, and the weights are modified from the weights that we used in the recombination section with the modification equation defined in equation 46. And the rank 1 update term is there to account for the sign information lost in the rank mu update. And it accomplishes that by maintaining a rolling sum on the history of update vectors with the equation defined in equation 45. And because the rolling sum is actually going to consider the sign information, its dot product square is also going to consider the sign information. So with that, we have both the old update and the sign information. And with that, we conclude our series on CMA-ES. If you want to see a simple demo and potentially play with CMA-ES yourself, you can check out the link to my blog, which I'm going to post in the description below. And I hope this video series has been helpful if you are in the process of learning CMA-ES. And if you have any questions,